These three problems are seemingly similar. A, B, and C are real numbers greater than or equal to 1, and their sum is 15. In the first exercise, without any other restrictions, is to prove AB plus BC plus CA is greater than or equal to 27. The second one, with an additional condition A, B, and C are less than or equal to 7, then the sum will be greater than or equal to 63. In the last problem, there seem only minor adjustment ABC less than or equal to 8 rather than 7. The minimum of the sum will be 62 instead of 63, but its proof is very different. The first problem is an easy one. A, B, and C are greater than or equal to 1 and their sum is 15. Prove that AB plus BC plus CA is greater than or equal to 27. A couple of observations. First, the equality holds when A, B, and C equals 1, 1, 13, or a permutation. 1 is the smallest possible values for A, B, C, and 13 is the largest. On the other hand, when A, B, C are all equal, the sum will be 75. This is the largest possible value, or the upper bound of the sum. It can be proved using the AM GM inequality. 27 is its lower bound, so this video is actually dealing with the other side of the AMGM inequality. The proof can be done by substitution. Let A equals A1 plus 1, B equals B1 plus 1, and C equals C1 plus 1. Then A1, B1, C1 are all non-negative values and their sum is equal to 12. Plug in the numbers, expand and rearrange the terms. The sum equals A1 B1 plus B1 C1 plus C1 A1 plus 2 times the sum of A1 B1 and C1 plus 3. Because the sum of A1 B1 C1 is 12, we end up with A1 B1 plus B1 times C1 plus C1 times A1 plus 27, which is greater than or equal to 27. And the equality holds when all the three products A1 B1, B1 C1, and C1 A1 are 0. In other words, 2 of A1, B1, and C1 are 0, and the last one must be 12 because the sum is 12. And the proof is done. The second problem is similar to the first one with an additional condition that A, B, and C are less than or equal to 7. So 1, 1, 13 in the previous problem are out of the range and the substitutions are no longer working. The equality holds when A, B, and C are 1, 7, 7 or a permutation. 7 plus 7 plus 49 equals 63. 1 is the lower bound of A, B, and C, and 7 is their upper bound. To prove it, we first introduce an inequality. A minus 1 times A minus 7 plus B minus 1 times B minus 7 plus C minus 1 times C minus 7 is less than or equal to 0. We know A, B, and C are all between 1 and 7, so all these three products are less than or equal to 0. So the inequality is true. But where is the inequality coming from? I mean, what is the idea behind it? As a matter of fact, its equality holds when A, B, and C are 1, 7, and 7 in an order. All three products must be equal to 0, so A, B, and C are either 1 or 7. But their sum is 15, so the only possibility is 1, 7, and 7. This is completely consistent with the target inequality, and that is why they are related. Expand and combine, we have a squared plus b squared plus c squared minus 8 times a plus b plus c plus 21 is less than or equal to 0. Therefore, a squared plus b squared plus c squared is less than or equal to 8 times 15 minus 21, which is 99. You can check the equality hold when A, B, and C are 1, 7, 7 in an order. 1 squared plus 7 squared plus 7 squared equals 99. Now, let's calculate A plus B plus C squared. This is a constant 15 squared. On the other hand, if we expand, it is a squared plus b squared plus c squared plus 2 times ab plus bc plus ca. We just established an upper bound for a squared plus b squared plus c squared. Then the lower bound for ab plus bc plus ca can be easily established. There are very minor changes on the third problem. A, B, and C are less than or equal to 8. To prove AB plus BC plus CA is greater than or equal to 62. This time, the equality holds when A, B, and C are 1, 6, and 8. Only two numbers are on the boundaries, 1 and 8. 6 is in between. So the approach solving the previous problem doesn't work. First, we keep one number C fixed and see how changing the values of A and B impacts the value of AB plus BC plus CA. But when changing A and B, they are still in the range between 1 and 8, and the sum of A, B, and C is still 15. When C is fixed, A plus B is fixed, and their average M is also fixed. If we write A equals M plus delta and B equals M minus delta, then delta measures the distance of AB from their mean. It is the driving force of the target value. Plug in AB plus BC plus CA equals A, which is M plus delta, B, M minus delta. Simplify the expression, that is m squared minus delta squared in the second and the last term, negative delta c and positive delta c cancelled. So we end up with m squared plus 2mc minus delta squared. As delta squared increasing, AB plus BC plus CA is getting smaller. Then how small it can be? We can keep increasing delta squared, then A and B become more and more far away from their mean until one of them reaches the boundary, either 1 or 8. Then we keep the boundary number unchanged and repeat the process for the other two numbers until one of them reaches the boundary again. Now, we have two numbers of A, B, and C on the boundary. They cannot be on the same side, either 1 and 1 or 8 and 8. Otherwise, the third number would be out of the range to come up with the sum of 15. The only possibility is 1, 8, and 6. Thank you for watching.